Hey guys, so today's lesson is on displaying and describing categorical data. So we're moving on from talking about experiments and collecting data for just a brief moment in this unit to talk about categorical data and how we describe it and display it and talk about it and all of that stuff. So today's objectives are going to read and interpret graphs based on categorical data. You're going to create graphs from categorical data, specific types of graphs I'm going to show you that you may have never made before, and then you're going to determine whether there is an association between certain categorical variables based on the data that we're given. So I'm going to start by just reminding you of when we're talking about numerical versus categorical data. So categorical data would be when we ask the survey question or we get the data from our subjects or from our sample, it is a category, a word, something like that. We also talked about how zip code would technically be considered a categorical variable because although it is a number, it is really kind of identifying where someone lives. So same could be said for area code or your student ID number or anything like that where technically it's a number, but it's really representing a category. So we kind of talked about that in the very first unit. I also wanted to remind you of our symbols for parameter versus statistic that we talked about. Some of you talked about it in the first unit and then a little bit in this unit as well. And we're going to practice kind of using them in an example here in a second. But if it's a means, which is numerical data, and it's a parameter, we use mu. For a statistic, we use x bar. With categorical data, we're dealing with proportions. So if it's proportions and it's the parameter, we use p. If it's the statistic, we use p hat. So for example, this was from an example way back in the beginning of the year, one of the first unit examples. But a neighborhood interest group wants to know what proportion of households in Austin watch the Netflix show Tiger King during the month of April 2020. They select a random sample of 59 households, find that 65.6% of those families watched the show, but in actuality, 72% of all households in Austin watched the show. So if I'm looking at the number 65.6%, because that is true for a sample, it would be a statistic that was of the 59 households, that's what percent of that sample watched the show. So that would be a statistic. And because it is a percentage or a proportion, the symbol that I would use for that is p hat. So the p with the little that guy over it. And then the 72% is what's true for the entire population. We just happen to know that. So that would be a parameter. And again, because it's still a proportion, it's still a percentage, the symbol we would use for that parameter is p, just lowercase p without anything over it. So that's just a little bit of practice, and I'll continue to kind of throw in these examples as we go through the lessons. So let's move on and just talk about categorical data specifically. So we're going to look at a couple of different ways to display that data. One really simple way is just with a simple distribution, right? Distribution, a table, you might call it, basically just names the categories and says how frequently each one occurs. So this is just a table form. So this is from the survey you guys filled out at the beginning of the year where I asked you what your favorite movies were. So I picked kind of a sample from that survey, and we had 16 liked comedy, 7 liked horror, 12 liked action, 5 liked drama, and 8 said another type. I think one of the other was I don't watch movies, so that was included in other. So this is just a distribution. It names the categories and then tells how frequently each one occurs. And we're really just looking at one variable right now. This is called a frequency distribution. We could also take that same data, and because we're just dealing with one group and each member of the group only picked one option, we could easily turn this into what we call a relative frequency distribution, which basically converts it into percentages. So 16 out of the total number in this sample gave us 33.3%. So 33.3% of this sample that I took liked comedy, 14.6%, that was just 7 divided by the total, liked horror, 25% liked action, 10.4% liked drama, and 16.7% said one of the other options. So that is a relative frequency distribution. So as we look at how to draw graphs just dealing with one categorical variable. One very obvious option is a bar graph. Now this is an example of a not very good bar graph. So this bar graph, it looks real cool. We got the popcorn going. It's like, oh, we're at the movies. I miss the movie theater, by the way. I know I've said that before, but I really want to go to the movie theater. This is what this makes me think of. But this particular graph, though it's very interesting, it is not a great graph because although we see the height of the popcorn buckets, the width of the popcorn buckets is also changing. Sorry, I can't talk this morning. So when we look at the graph, we're taken up by the area of the popcorn buckets and not just the height. So although like this popcorn bucket is twice as tall as this other one, it looks more than twice as big because its width is changing as well as its height. So when we do bar graphs, we want to stick with something. It's okay to use graphics here and there as long as they're not too overwhelming, but we want to stick with something that's going to keep the same width and have different heights. Or if you have a bar graph going the other way, which is a thing, you would want the bars to have the same kind of height and then be longer or shorter from left to right. So that way we're really kind of visually just seeing the change in height as opposed to the change in width as well. So we're not like distorting what's really true. Okay, so a bar graph or bar chart displays the distribution of a categorical variable, showing the counts for each category next to each other for comparison. With a bar graph, we have these gaps in between because that means there's no real like sequence of our categories on the bottom. We could easily mix these around and that would be totally fine. It would still mean the same thing. A lot of times a bar graph will start with the tallest and move down to the shortest. But in this case, I didn't do that. A good bar chart stays true to the area principle, which basically means our width is staying the same and then the only difference is the height. Like I mentioned, for categorical data, for bar charts or bar graphs, we do want to leave spaces in between the categories because that indicates that these are separate and there's no real sequence to them. And that's different for a numerical graph that we'll talk about in the next unit. Okay. So we could also have what we call a relative frequency bar graph, which displays the relative proportion. So instead of counts on my y-axis, I now have percentages. Notice that graph looks more or less the same. The only difference is my y-axis is percentages. But if that's the information we have, or if we wanted to see the percentages of the total, we could do it that way as well, and it would mean the same thing. So when we are looking or describing or talking about a graph that we're given, we want to make sure that we do notice what is on the y-axis. For this example, we have a bar graph that shows the percentage of drivers in each region that wear their seatbelts. Notice that these percentages don't add up to 100 because we are talking about 4 different regions. So like it's talking about what percent of that region wears their seatbelts while driving. This is an old graph, by the way. Hopefully this data has changed. So if a question asked you, in which region do the greatest number of people wear seatbelts, you might be tempted to say, oh, it looks like West. But remember, we are given percentages on this graph. So although West, we can say, has the greatest percentage of drivers who wear seatbelts, we don't know how many people are in each region or how many people were in the samples that were taken from each region. So I don't know for sure that West actually has the greatest number because I don't know. Maybe West had a really small sample size and the Northeast had a really big sample size, or there's more people. So we can't really say number based on this graph alone. So all we could talk about is that overall, all 4 regions have over 60%. A lot of times questions will ask you to compare and contrast. So we could say all 4 regions have more than 60% of drivers wearing seatbelts, and that the Midwest has the smallest percentage of drivers wearing seatbelts, while the West and South kind of have the largest percentage of drivers wearing seatbelts. So those are things that we could say about this graph because that's what we're given. So always pay attention to the graph that you're given and really kind of look at those details before you start describing it. Because you want to make sure you're describing it in the correct context. In this case, the word percentage or proportion as opposed to the word number. We could also draw a pie chart. This is really good for when we're interested in parts of a whole. So if we have one population that we asked one question and there's no overlap, like one person in my population couldn't answer 2 options, they can only answer 1. This is a really good option for that. So I said that here. It only works when you're looking for the distribution of one variable for one population where they're not allowed to say more than one option. So this is showing me the different percentages of people who liked each type of movie in our sample. So those are ways that we can just distribute or show the distribution of one categorical variable. But a lot of what we deal with when we're talking about graphs or information from categorical variables is looking at or comparing two categorical variables. So for that, we can have, instead of just one single table that shows the distribution of one variable, I could have what we call a two-way table, which allows us to look at two categorical variables together and see how those two relate to each other. Okay, so firstly, know that these total column and rows are known as the marginal distributions. Sometimes you might be asked, what's the marginal distribution for movie type? In which case I'd be looking for what's the total of each, movie genre or movie type. So this categorical or contingency table is looking at the relationship between the movie genre that someone likes the best and whether they categorize themselves as less funny or more funny. So one of the questions asked on the survey that you guys took, how funny are you on a scale of 1 to 10? So the less funny I did was like 5 or less, and then the more funny was 6 or more. So that's kind of where I got those numbers, but we're kind of looking to see if less funny people have differences in what movies they like compared to the more funny people. And again, this was just from a sample from that survey, right? So marginal distributions are just referring to what's the totals. We could also use this graph to find simple percentages. So if I asked what percent of the students in the survey are less funny or categorize themselves as less funny, so total we have 15 less funny out of 48. So that would be about 31.25%. So just divide it and then either multiply by 100 or move the decimal place over 2 places, whichever one you want. If we left it as 0.3125, that would be the proportion of students who are less funny. If I ask what proportion of the students are more funny and like action movies, I'm kind of looking for an intersection. So more funny and like action movies, that's 7 people out of the 48 total, which is 0.1458. So that's what makes it a proportion, is just that we leave it as the decimal. If I ask what percent of the more funny people like comedy. So now I'm saying not of all the students, but only of the more funny people. So always look for, my hint is to look for the word of. So of is going to tell you what number goes on the bottom of the fraction. So of the more funny people, of those 33 people who categorize themselves as more funny, what percent of them liked comedy? So in that more funny row, we had 15 out of the 33 who said they liked comedy the best. So 15 out of the 33 is 45.45%. And then last but not least, I could ask what proportion of people who like comedy movies are more funny. So of the people who like comedy movies, not of all the students, but of the people who liked comedy movies, which is 16, what percent of them categorize themselves as more funny? So of those 16 who liked comedy, 15 said that they were more funny. So 15 out of 16. So 0.9375, 93-ish percent, 94% of people who like comedy movies categorize themselves as more funny. Who knew? So that's one thing we can do with those two-way tables is calculate just kind of basic percentage and proportions from the data. We have to pay attention to the of statement to know what we're talking about. Another thing we can do is divide up our table into what we call a conditional distribution. So a conditional distribution kind of looks at kind of separates one of those categorical variables and looks at what are the distributions within each of those options for that category. So for this example, I separated based on the condition of funniness. So looking at, okay, so out of the less funny people, I want to know what percent liked comedy, horror, action, drama, or other. And then of the more funny people, what percentage liked comedy, horror, action, drama, or other. So I'm separating it on the condition of funniness. Now I could also separate this table the other way, and I could have split it up into 5 separate tables for comedy, horror, action, drama, or other, and within each genre figured out what percentage of that genre categorize themselves as less or more funny. So I could have split it up the other way, I just chose to split it up this way. So in my less funny section, 1 person out of the 15 categorize themselves as less funny. So 1 out of 15 is 6.7%. And then I continue to do that for all of the numbers. So horror, 3 out of 15 is about 20%. For action, 5 out of 15 is 33.3%. 0 out of 15 liked drama in that category, in that less funny category, so 0%. And then 6 out of 15 is 40%. For the more funny section, same thing. I did 15 out of 33 is 45.4%. 4 out of 33 is 12.1%. 7 out of 33, 5 out of 33, 2 out of 33 to get these percentages. And that kind of lets me look at each category, kind of splitting it up into two separate samples or two separate populations, and looking at within each category what percent liked the different genres of movie. And this kind of gives me a little bit more information. I can see that less funny people are a whole lot more likely to say other compared to more funny people. Right? 40% of the less funny people said an other, and then the more funny people, only 6.1% said other, right? More funny people were much more likely to say that they liked comedy the best. Imagine that. So 45.4% of the more funny people said they liked comedy versus only 6.7% of the less funny people. So we're able to kind of compare really well in terms of percentages. Now I could take that conditional distribution and use a side-by-side bar graph. I just use counts on this one, so this is just numbers of students. A side-by-side bar graph, basically just, we still are separating each category, but now I have one bar that represents the less funny people and one bar that represents the more funny people. And I could do that for each type. And this would give me just a quick look at the numbers, and I could compare the numbers. But this kind of graph, although it is a really quick and easy one to draw, doesn't necessarily show us what we call association. What we have to be careful of when we're dealing with a side-by-side bar graph or a conditional distribution is realizing that in this case especially, I have different amounts of people. So just looking at the numbers might be a little misleading, right? We could say only 6 people that were less funny said other. That's not very many. But when I realize that I'm only dealing with 15 people total, right, versus 33, those numbers are going to be a lot different. So we have to make sure, and we're looking at the percentages if we wanted to talk about association, which we will in a minute. We could also draw a pie chart using those separate percentages. Again, because we're separating it into less funny and more funny, we're kind of dealing with two separate samples. So I can look at what percentage of each little sample liked each type of movie. And that would give me a good way to visually compare those percentages. And I can see, wow, almost half of the more funny people like comedy versus a really tiny sliver of the less funny people. So it allows me to see those things really quickly. Another thing we can draw, and this is a really good way for you to draw on paper if you needed to draw a graph that showed the percentages, because it's a lot easier to draw than a pie chart where you have to kind of figure out how big the slivers should be. So a good way to draw those percentages is to use what we call a segmented bar graph. It displays the same information as a pie chart, which is percentages, but in the form of bars instead of circles. So I have my percentages here from my conditional distribution that I did a minute ago, right? So I'm just going to make this kind of long or tall bar chart or bar graph area. I have my two categories, less funny and more funny, so I'll create two different bars for two groups. And I'm basically going to be stacking the sections on top of each other. So for less funny, 6.7% of them liked comedy. So on my y-axis, I have percentages from 10 or from 0 to 100%. So less funny, the comedy section was 6.7%. So I could draw a little bar. It's like about 6.7%. And then when I go to draw the horror bar, that sounds crazy. What I have to be careful is I want that percentage of that bar to end to where that whole bar represents 20%. So what I kind of do is add up as I go. So 6.7% plus 20% gives me 26.7%. So I know that this bar should be ending at about 26.7%. Right? And then I can do the next one is 33.3%. So if I add all those percentages together as I go, we know that this one should end at about 60%. And that yellow section is representing that 33.3%. There was nothing for drama, so I'm not going to put anything for that. And then my remaining other 40% should bring my bar up to 100 to represent that this is 100% of the less funny people. And I can do that same thing for the more funny people. I want to always make sure I'm including a key, so I drew a little key to explain what each section is. And then I'm going to do the same thing for the more funny people. So I have more funny, right? all my little sections that add up to 100, and I did that same thing. So this bar graph allows us to really compare the percentages. It's a really quick and easy thing to draw on a sheet of paper, which is what you're doing on the AP exam, compared to having to draw a circle and figure out like how big each section should be to make it accurate. You don't really have a protractor on the AP exam, so this is a really good way to draw that quick bar graph to compare percentages, which again, if we're going to talk about association, which we're going to, we want to make sure that we're dealing with percentages. So for this sample, this is a question you could be asked. For the sample, does someone's funny rating, how funny they rated themselves, seem to be associated with their preferred movie genre? So when we are asking that question, we want to make sure we're looking at percentages. So in other words, does the funny level that someone rated themselves seem to have an impact on what genre of movie they preferred? So if I'm looking at just the numbers, it's going to be hard to tell, right? But we have to make sure we're looking at percentages because the numbers in each section of less funny and more funny are different. It wouldn't really be fair to talk about the numbers. I could say like, oh, it looks like horror is about the same for both groups because 3 and 4. But really, if I'm looking at percentages, I can see that a much bigger percentage of the less funny people chose horror. So even though those numbers look similar, when I look at the percentages, I can see that they're different. So if I'm going to talk about association, I need to make sure I'm looking at percentages. So I could say the funny level and movie genre are associated or are dependent because the percentages of each genre are different for the less funny and more funny people. So that kind of tells me that what they rated themselves as in terms of funniness is seeming to have an impact. You see that change in percentages, that distribution of percentages is different between the two groups. And I can see that with my little segmented bar graph as well. I can kind of compare and see that the blue sections in terms of percentages are way different. So that kind of tells me that there's an association, that there's a difference between the two groups. So your funny rating is associated with what genre you like. Okay. The variables would be considered independent or not associated if the relative percentage distribution or the percentages of movie genres were roughly the same for both funny categories. So if we saw about the same percentage of less funny and more funny people liked comedy and horror and action and drama and other, if those percentages were the same for both groups and every single movie genre, then I could say that there doesn't seem to be an association, because that would basically mean it doesn't matter how funny you are, you're going to like the same types of movies regardless, or like the percentages are the same. So this is a little quick cheat sheet. Let me go back to it. If you want to screenshot that or copy that down, we say that it's independent or no association when the percentages of one variable are the same for all categories of the other variable. And then we say that they are dependent, or there is an association when the percentages of one variable are different for some or all of the categories of the other variable. So if there's any differences in any of those categories, we say that they are dependent. Okay, so just to show you an example of one that is independent, this is looking at, for a sample of people, their gender versus how much education they have. So if I'm just looking at the numbers, I might be tempted to say like, oh, more males were not high school graduates. Those crazy males. But also more males than females were high school graduates, and more males than females were college graduates. Wait a second, there's just more males in this survey. So just looking at numbers is misleading, and it's not really telling us whether there's an association between gender and what level of education someone has. So if I instead look at the percentages, so I'm dividing this up by the condition of gender. So I looked at males and females as kind of two separate samples and found what percentage were in each level of education within each gender. And I can see that those percentages are the same for males and females, and that it's the same as the overall percentages. This kind of tells me that there is not an association. Sorry, I said that funny. If I just look at a bar graph that's dealing with numbers, again, it's misleading. It makes me think that males are more likely to do all three of these categories, which doesn't really make sense. So if I'm looking at a segmented bar graph, for example, I can see that those percentages are exactly the same for both males and females. So we would say that gender is independent of level of education, meaning it doesn't seem to matter what gender you are, your level of education or your chance of having a certain level of education is approximately the same, right? No matter what. So they are independent, there's no association. So I know that was much longer of a video, so thank you for sticking around, and I will see you guys next class.